Okay, so I'm going to talk about different ways that you can find out a turning point of a quadratic curve if an equation y equals to certain ax squared plus bx plus c is given. Now, the turning point usually is where the gradient of the quadratic curve will be zero, not as quadratic any curve, but the turning point is where this thing will actually change direction here and the gradient will become zero, being parallel with the x-axis. All right. And the typical thing about quadratic equation is that it should actually have a maximum of two solutions. There is no way we can find out three different roots from a quadratic equation. So that's main thing about quadratic equations. One thing I mean, obviously, I wanted to do a video on the different methods of solving a quadratic equation, but this is not that for time being. I'm just going to talk about the turning points. Now, in both Maslow and ATMOS, you have actually seen different methods of finding turning points. All right, completing square, then we have differentiation. Mainly these two are quite known. However, here's another thing. There are actually two more methods which may or may not be allowed, but are actually quite useful in some places. This is what I realized in one of the past syllabus I was trying to do, probably 2016 or 2014. In that case, it was given an equation like this. I mean, let's say something like this, and then you had to find a turning point of this thing. So yeah. Anyways, I'm just going to show you the method. I mean, let me show the first two obvious methods, the ones everyone know. Then I'm going to go on to less obvious ones. Number one, which is completing square. Now the turning point is where the value of x and y, I mean the value of this equation, the solution to this equation will be minimum or maximum. If that's the case, then we can find out that where that is on x in terms of x and y. That's what we call a vertex point. Anyways, y equals to 4x squared plus 8x minus 5. I'm just going to put this example as my test here. So, I mean, this is what I'm going to use for all of the equations out there. Now, y equals to, so the way you do this is by taking 4 common out of these, and then you just write x squared plus 2x minus 5 by 4. And then you can do one or two things. You can either use a direct formula, x squared plus ax equals to x into sorry, x plus a by 2 whole square plus a by 2 whole square, or you can just break this down further. X square plus x 2 into x into 1 plus 1 square minus 1 square minus 5 by 4. Now the reason I did this is because I want to write this in the perfect square form. And also you'll notice that I actually put a minus here. This whole thing is actually part of the perfect square formula, but then because I do not have this thing, I have actually put a minus here. I do not have this one, so I put a minus to compensate that. And I divided this one by 2, divided this one by 2, so that I can actually make sure that if I multiply this with this, I can get this 2 right here. All right, let me show you again. I divided this thing by 2 to get this one, so that if I multiply these two together, then I'll get this 2 here. So that's what I've done. Now, let's just do it as fast as possible. So, I can write this whole thing in form of a perfect square. Minus 1 minus 5 by 4. So we get 4 times x plus 1 whole square, x plus 1, right? Minus 9 by 4. So we get 4 times x plus 1 whole square minus 9. Now, what's the turning point from here? This value, ignoring no matter if it's plus or minus, will always be the turning point. So the turning point will be this minus 9, and it's only going to happen if this whole thing is equal to 0. X plus 1 whole square equal to 0. So we get x equals to minus 1. That's the turning point. This is method number 1. So by completing the square, you can just get into this form, And then from here, you just do this thing equal to 0, you get x equals to -1, or you can, and then you can just find out the y value, which is going to be directly this one here. And obviously, you should be able to distinguish if it's a maximum or a minimum by just looking at the coefficient of x, or simply in this case, if this coefficient before the perfect square is positive. So that's the way we can do this one. Method number 2, calculus. Calculus as in differentiation, to be more specific. Among the two, this is the simplest of both, but I mean, this is the simplest to work with, and obviously, this is something most people would think the simplest to deal with, simplest to understand. However, there are some other simpler methods than this one, which I'll show you later. Okay, so I'll go back to my previous equation again. Y equals to 4x squared plus 8x minus 5. So here, as I mentioned, you just try to do differentiation here. So obviously, you just need to do dy dx. So dy dx equals to 2 into 4x plus 8. So basically, you just bring this power to the front, and then you subtract 1 from this power. So you get 2 into 4x plus 8. So we get here 8x plus 8. Now, from there, you can do the following. Equal to 0, because as I said, this is when the gradient of the curve equals to 0. So basically, we know that dy dx happens to be the gradient, so we can just find out that this equals to 0. So as a result, we'll get 8x equals to minus 8, x equals to minus 1. Now, because we know that the turning point will have an x equals to minus 1, we'll just substitute this back into the equation here. So we get y equals to 4 into minus 1 whole square plus 8 into minus 1 minus 5. So we get here 4 minus 8 minus 5. 4 minus 13 equals to minus 9. So the turning point is minus 1 minus 9. So this is the way we do turning point for calculus. Now, this is actually simpler than the completing square, but it's not as simple as the method. I mean, okay, let's not do a whole lot of cliffhanging here. We'll just move on. Now, number 3 is something that is not known to a whole lot, right? So so basically these methods that I've just shown you are your normal methods of algebra and calculus, right? This method is geometrical, which is where you have to have the knowledge of symmetry, right? So this is the geometrical method. Now, how does this geometrical method work? Well, let's just imagine a random quadratic curve, all right? So you realize that basically, if it happens to be a general quadratic curve, we know that for a quadratic curve, if we have a certain value of x, sorry, if we have, let's say, certain value of y, there will be two values of x. So if I imagine the equation y equals to x squared, let's say. And if I substitute x equals to -1 and x equals to 1. So we get y equals to -1 whole square equals to 1, y equals to 1 square equals to 1. So it means that on the quadratic curve, you have something like this, where the curve will have the same value of y for two different values of x. Let's say it is 1 here, -1 here. This is the value of y corresponding to it. Y equals to 1. When this is -1 and this is 1. Similarly, we have this one, these two values corresponding to the same thing, these two values corresponding to the same thing, and so on, and whatnot. Now, because of this is going to be the same, and these two are going to be the same. So we can technically say that if these two are same, their distance from the y-axis will be exactly the same, right? And in this case, you'll also realize that the turning point of this x square thingy will be the origin. So the distance from the origin to the two points of two values of x, which will correspond to same value of y, will actually be the same. Because of this, we can easily say that any quadratic curve, not just this one, any quadratic curve that has a turning point, I mean, obviously all of them do, but from the turning point, the distance from the distance from a turning point to a certain two corresponding values of x giving us certain value of y will be the same. So this is always applicable for a certain value of y corresponding to two different values of x, right? A certain value of y will correspond to two different value of x covering the same distance. If that's the case, I can easily say that we can easily say that the quadratic curve is symmetric. Quadratic curve is symmetric about its turning point. So one thing that is for sure, if this happens to be the turning point, then from the turning point, this will turn out to be the line of symmetry. Okay, ignoring the line of symmetry, one thing that's for sure, if the distance from the x values, I mean, if the distance between the roots of the x values to the certain line of symmetry is going to be the same, then obviously these two are in the ratio 1 is to 1. We can then use the coordinate geometry again. These two will be at the same distance. This will be the midpoint at the x-axis. So this will actually help us to determine the x coordinate of the turning point, because that's what we talk about when it comes to the line of symmetry. For y equals to something x squared plus bx plus c. If it's x equal to a y squared plus by plus c, that's the different thing. But for this case, as a y which is dependent on x, this is going to be a different case. All right. Actually, let me just do this on the next page. Okay. So here we go. Now let's just talk about the actual point again, actual curve again. So coming back to this equation, we'll notice that we do not have anything that we can do with the roots basically. So if what we can do is that if we happen to know the value of the roots, then we can actually find out the midpoint of the two root values. That's going to be the point of the that's going to be the x coordinate of the turning point. And then so just like differentiation, we just substitute this back. Now, there's actually a bit of a similar trick here, which we'll do in number 4, but it's actually a very much of a direct approach. I'll show you later. So y equals to 4x squared plus 10x. Okay, not 10x, I'll just do 2x first because that's simpler. Plus 10x minus 5. So therefore we have 2x, 2x minus 1 plus 5, 2x minus 1. So we get here 2x minus 1, 2x plus 5. So 2x plus 5. So therefore x equals to half, x equals to minus 5 by 2. Now, from there we can just try to find out the midpoint. Midpoint or mid value of x is going to be the average of these 2 points. So we get here minus 4 by 2 divided by 2. So we get here minus 4 by 4 minus 1. Now the substitute is back into this equation and we get the same answer. There we go. So the turning point here is going to be minus 1 minus 9. Now, number 4 is the OP direct approach, which you are not really meant to do at all unless or otherwise there's not enough workings necessary to be shown. All right. I call this OP direct approach. Why? Look at this. I'm just going to show a bit of a derivation here first, where this comes from, and then I'm going to show you how you can use this one. So just let's just go back to the standard form of quadratic equation. If we differentiate this one, we'll be able to find out the exact x coordinate where we have the turning point. This equal to 0. So we have 2ax equals to minus b, x equals to minus b by 2a. What does this mean? It means that if I have a certain case where we equate the gradient of this curve equal to 0, we will always have this fixed form of value of x, which will give us the value of the turning point of, x coordinate of the turning point. Yeah. So, okay. So that's basically that. It means that for any case that we have a turning point, we just have to use this formula. So guess what? If I have this form, substitute it there. Use this value as a, this value as a b, and then substitute it there. You just substitute. Okay, that's a bit too light. You just substitute x equals to minus 8 divided by 2 times 2. Sorry, 2 times 4. So we get minus 8 by 8 equals to minus 1. Now the substitute y equals to this thing back again to this equation like before, and we get 4 minus 8 minus 5, 4 minus 13 equals to minus 9. So really the quadratic equation is the only sweet spot where we can actually do quite some methods of finding the turning point. Had it been any other equation out there, like cubic or quartic or exponential or whatever, we would not be able to use this form. We would have to move on with the uh, differentiation approach. But yeah, this is the direct approach I was talking. I am talking about. So yeah, basically that's the way you can solve these quadratic equations. So yeah, that's basically it. Thanks for watching.